Hello everyone, this is Aris. Today we'll talk about linear vector spaces. We have used the vector r to mean a vector from the origin to the point xyz. There's a one-to-one correspondence between the vectors r and the points xyz. This collection of all points xyz of all vectors r makes up the three-dimensional space often called R3 or V3 or E3. R for real, or V for vector, or E for Euclidean, but they all mean the same, the three-dimensional space. Similarly, we can consider a two-dimensional space V2 of vectors R. Here you have I hat x plus j hat y, or points xy making up the xy plane. Um, V2 also means any plane through the origin, and V1 means all vectors from the origin to the points on some line through the origin. Generally, we can call an ordered set of n numbers a point or vector in the n-dimensional space Vn. So we here this is a more generalized um, treatment for vector space. Such examples that exist in physics are the space-time in special relativity. So you have V4 is four-dimensional. You will also encounter phase space where you have um, six coordinates, three components for position, three for momentum. So there's a total of six. It's a six-dimensional space, V6. Geometrical terminologies familiar in 2 and 3 dimensions can be extended to n dimensions. So for example, you have a distance from the origin to point xyz. The distance is x squared plus y squared plus z squared. You take the square root. In 5 variables, x, y, z, u, v, the distance from origin to that point, x, y, z, I, this is u. Okay, that's u, v. This would be x squared plus the square root of x squared plus y squared plus z squared plus u squared plus v squared. Example, find the distance between the points 3, 0, 5, minus 2, 1, and 0, 1, minus 2, 3, and 0. So the distance squared is just, let's say we take the difference of corresponding components, 3 minus 0 squared plus 0 minus 1 squared plus 5 minus negative 2 squared plus negative 2 minus 3 squared plus 1 minus 0 squared. This would be 9 plus 1 plus 49 plus 5 squared, that's 25, plus 1. 1 plus 9 is 10, 49 plus 1, that's 50, 50 plus 10, 60, so this is 85, or you take the square root, the square root of 85. That is the distance between these 2 points. If we start with several vectors and find linear combinations of them, then we say that the original set of vectors and all their linear combinations form a linear vector space. Sometimes you can also call it just vector space or linear space or simply space. If you have two linearly independent vectors, they determine a plane, and all linear combinations also would lie in that plane. Since all the vectors making up this plane are also part of the three-dimensional space V3, we call V2 a subspace of V3. If you have a line passing through the origin along this plane, lying in this plane, is a subspace of V2 and V3. Linearly independent vectors or linear combinations of them span the space. So a set of vectors spans a space if all the vectors in the space can be written as linear combinations of the spanning set. That's the definition of this term, span. A set of linearly independent vectors which span a vector space is called a basis. And um, the number of basis vectors, that's the dimension of the vector space. Now let's consider three quantities: inner product, norm, orthogonality. The inner product of two vectors A and B um, in n dimensions is defined by A dot B given by, and then you use the summation of AI times BI where I runs from 1 to n. In We can define the length also or norm of a vector in n dimensions by this formula. So A, norm of A, here you have two vertical lines here. Take the square root of A dot A, so you get this. In n dimensions, two vectors are orthogonal if their inner product is 0. So you just solve for the inner product. If that is 0, then they are orthogonal. There's something called uh, Schwarz inequality for n-dimensional Euclidean space. It's given by this expression that you take the absolute value of A dot B, this is the distance or the norm um, of the inner product A dot B. That's less than or equal to magnitude of A times magnitude of B, or written like this. We can be able to prove this, for example, or in a specific case where B is equal to 0. So if B is equal to 0, write that properly. If B is equal to 0, then RA dot B less than or equal to AB, simply 0 less than or equal to 0, which is correct. Now for B not equal to 0, let's use a form of for some vector. So we consider the vector C given by magnitude of B times A vector minus A dot B and B times B divided by magnitude of B. This is just some vector of this form where B and A are the B and A here that we want to write in this expression. So if we take C dot C, that would be just sum of all I of Ci squared. This is greater than or equal to 0. So C dot C, if you use this, that would be B squared A dot A, this by itself, minus this times this and this times this. That's twice of um, B A dot B times A dot B divided by B just B plus this squared. So you have A dot B, B dot B. That's right. That's B dot B divided by B squared. Is B dot B, B squared are just the same, so they cancel out. So here you have this is A squared, B squared minus B, B cancels, so this is 2 A dot B um, squared plus here this a dot b should be for this part here should be squared, so this is squared. B dot b squared, they cancel out, so you have a dot b squared. So a dot b squared minus 2 a dot b squared, so this gives you a squared b squared minus a dot b squared. And recall that this is equal to c squared, and c squared is greater than or equal to 0, which means that a dot b, if you take the absolute value of that or magnitude of a dot b, um, so a dot b squared is just the magnitude of a dot b squared. You take the square root, you also take the square root of this two, so you can write a dot b absolute value or the magnitude is equal to square root of this times square root of this, and that's what we want to show. Okay, that's our Schwarz inequality here. Other definitions: we call a set of vectors orthonormal if they are mutually orthogonal, and each vector is normalized if it's normalized. It means that the norm is 1. For example, the vectors I, J, K form an orthonormal set. If you have a set of vectors, basis vectors for a space, it is convenient to take combinations of them to form an orthonormal basis. We do this using Gram-Schmidt method. In 3 dimensions ABC, we follow this following steps. We normalize A, so in that case we get the first orthonormal basis um, vector, so the first one. The second one, we subtract B from its component along A. So what would happen is if this is B and this is A, so we take the component of uh, B along A. So for example, this you project B to A, so we'll say B dot A. Okay, to get a vector orthogonal to A, when we subtract B minus B dot A, okay, so B minus B dot A, that would be this vector, and that would be perpendicular to A. And then we normalize that, that would be our second orthonormal basis vector. And then lastly, we subtract C from its component along A and B. So C minus C dot A minus C dot B. And this will be, we normalize this, it will be the third orthonormal basis vector. In higher dimension, we simply continue the process. We keep subtracting with the vector component along the next or the previously used vectors. For example, given the basis vectors A, B, and C, use the Gram-Schmidt method to find an orthonormal set we call E1, E2, E3. So using our A, we normalize A. Okay, so normalize A to give us E, so that's E1 equals A. To normalize, if the norm of A is not 0, then we divide A by its norm. Or the norm of A is not 1, then we divide it with its norm. So you have 0, 0, 5, 0. The norm would be 5. So if you try to solve, the answer is 5. So E here is 0, 0, 1, 0. That's our E1. For E2, we take so to solve for to get E2, we subtract from B the component of um, A or B along A. So we take the dot product of this to this, or we can also just make use of this um, this basis orthonormal basis vector. So we have B or E um, dot B. Okay, that's the magnitude of the component. By the way, here this is a uh, this is not a vector, so we will need a direction of A. Um, I will normalize this so that um, you simply get the direction, and here you use the direction of D. Okay, just to be clear, here we're only using um, the normalized form, so we simply multiply this by E. Okay, and this would be B minus E1 dot B, that would be 3 E1. B is 2030 minus, so this is 0030. That gives you 2000. So we normalize to get E2. So we normalize this to get E2. So that's 2000 divided by the norm is 2. So that's 1000. That's our E2. And finally, for C, we simply subtract from C um, E1 dot C times E1 minus E2 dot C times E2. Okay, C C is this 71 minus 53 times E1, that would be um, just this -5 here. So you can write C um, plus 5 E1 minus, so for E2 it would give us only that 7. So there's 5 times E1, so there's 5 here, minus 7, there's a 7 here. So originally we have 7 1 minus 5 3. You remove 7 because of this -7 and positive 5 5. So you have 0 1 0 3, and then we normalize to get E3. So E3 would be 0 1 0 3 divided by the norm of this would be 1 squared plus 3 squared, that is 10 square root of 10. That's our E3. In a complex Euclidean space, we can also write our inner products norms, orthogonality here, equation, um, using or specifying generally for a complex Euclidean space. The Schwarz inequality becomes like this. Basically, we add on the first vector a complex conjugate. Example, given A, B, and C vectors, find the norm of A, norm of B, inner product A dot B, inner product B dot C. For the norm of A, that would be complex conjugate, so minus 3i times 3i plus 1 plus I, 1 minus I, 2 plus 3i, or 2 minus 2 plus 3i, plus 1 minus 2i, 1 plus 2i, take the square root. This would be minus 3 times 3i, so that's 9. 1 plus I, 1 minus I, that's 1 plus 1, so that would be 2. 2, or this becomes 2, 2 times 2, 4, plus 3 times 3, 9. That's 13. 1 plus 4, that's 5. So the norm of A would be 29. Okay. For B, the norm would be, so you do the same thing. 1 1 plus 2i, so this would be 1. This would give us 5. This we'll get 10, and then here you got 1, so 1 plus 5 plus 10 plus 1, that's 17. You can work that out yourself to check. How about A dot B? A dot B, for A you have 3i, but that becomes complex conjugate, so 3i, B is minus 1, plus 1 plus I, B is 1 plus 2i, 2 plus, or 2 minus 3i, 3 minus I, 1 plus, or 1 minus 2i times I. Okay, 3 minus 3, so that's simply 3i here, plus 1 plus I times I, that 2i times I, so that's 3i minus 2, 2i to I here, plus here 3 times 2, that's 6, 2i, so negative 2i, negative 9i, so that's negative 11i, minus, so it's minus 3i times minus I, that's 3i squared, so minus 3. Finally, you have plus I and plus 2. Okay, so you have 3i, 3i, that's 6, um, minus 11i, that would be minus 5, and then I, that's minus 4i, 1 minus 2 plus 6, so that's 5, minus 3, that's 2 plus 2, 4. For B dot C, you have B is negative 1, C is 4 minus 2i, then 1 plus, or 1 minus 2i, and then 2 minus I, plus 3 minus I, complex conjugate 3 plus I, and here it's 1. And then here, negative, that's I here, complex conjugate, negative I, and finally I minus 2. Okay, so this is negative 4 plus 2I. 1 times 2, it's 2. 2I times 2, that's negative 4I. 1 times minus I, that's negative I. So this would be negative 5I. Minus I minus 2I, so that's minus 2. Okay, or 2I squared minus 2. Plus, you have 3 plus I here. And then finally you have plus 1. Okay, I. And plus 2I. Okay, so minus 4, 2, that's minus 2, minus 2, that's minus 4 again. 3 plus 1, that's 0. 2I minus 5I, that's 3I. Minus 3I plus I, that's minus 2I, plus 2I, that would be 0. So the inner product of B and C are 0, which means that B and C are orthogonal.